Assalamualaikum warahmatullahi wabarakatuh, and good morning to my lecturer Dr. Kok Kun Siong and to all my classmates. Today I am going to present my task 3 project for computational thinking in mathematics. Before we look at the maths, I want to start with our big idea for this task, which is sustainable problem solving through parallel computational thinking. We also have two questions that will guide us today. How can we solve complex problems with maximum efficiency, and how does decomposition change the way we view mathematical challenges? Today, I will answer these questions by showing you a heuristic, a problem-solving strategy called the sorting network. I am Ahmad MIRZA bin NIZWAN, and this is how we solve non-routine problems. First, we need to know what a non-routine problem actually is. So, non-routine problems are problems that lack a clear, immediate procedure or formula for a solution. They require creative and adaptive strategies, according to Obando Montoya et al. 2026. Look at the mindset matrix on the screen. When we were in primary school, most math was routine. You get a formula, you plug in the numbers, and you get the answer. It relies heavily on memorization. But a non-routine problem is different. According to 2026 study, also by Obando Montoya and his team, non-routine problems do not have a clear, immediate formula. You cannot just memorize a step to solve them. They require higher order thinking skills or HOTS, and they often have multiple solution pathways. If you look at the routine problems, it is using a known formula to reach an answer, relies heavily on memorization, and also only use single solution pathway. As future teachers, this is important. Ravik and Opsal 2026 state that we need to teach our students adaptive strategies, not just how to be calculators. We need them to be problem designers. Let's put this into a real-world 21st century context. Let's look at our scenario. Imagine a large logistics company. They have thousands of packages arriving every minute, and these packages must be sorted by weight. If they sort them one by one, it is too slow. For our specific problem today, we have a mission. We must sort 6 packages by weight as fast as possible. But we have strict constraints, which are our comparison stations can only weigh and compare 2 packages at a single time, and we can only operate a maximum of 3 stations simultaneously. This is what we call parallel processing. The question we must answer is, what is the most efficient configuration to guarantee all 6 packages are sorted correctly, and how many time steps will it take? If you just look at this problem, there is no simple formula like A plus B to solve it. We have to build a heuristic using computational thinking. To build our solution, we apply the first 2 pillars of computational thinking. First is decomposition. Looking at 6 packages moving at once is confusing. So we break it down. Rahmana Encourages 2026 explained that decomposition reduces our mental load. We break the entire warehouse problem down into one simple action, comparing just two boxes. One box goes left, one box goes right. That is our basic unit. Second is pattern recognition. During our unplugged activities in class, we noticed a pattern. The action of comparing and swapping is exactly the same at the beginning of the line as it is at the end of the line. Because the pattern repeats, we can copy and paste this simple action to build a larger system. Purwasi 2024 notes that finding these patterns is how we scale a small idea into a big solution. Next, we use abstraction. As you look at the screen, abstraction means ignoring the noise. I do not care if the packages are big, small, red, or blue. I do not care who is driving the forklift. Araya 2021 tells us to focus only on the data. So, I abstracted the physical warehouse into a mathematical node network graph. The lines are the paths the packages take. The boxes or nodes are where the comparisons happen. By making it abstract, we turn a messy physical problem into clear, pure logic. Now, we come to the most important part, the algorithms. Usually, an algorithm is a step-by-step list. First, do step 1 and then step 2, but we are using a parallel algorithm. Multiple steps happen at the exact same time. The rule for our algorithm is simple. When two numbers enter a node, the smaller number will always take the left path and the larger number will always take the right path. So, as you look here, if input A is bigger than input B, they swap path, which is the smaller value exits left, the larger value exits right. If not, they continue straight. Because of how we connect the nodes, the packages will sort themselves automatically as they move forward. For the reliability, this algorithm ensures a perfect sort regardless of the initial starting order of the data. Obando Montoya et al. 2026. To truly understand this, I am going to do a live trace. Let's look at the picture here of our 6 packages which have the weights of 9, 5, 1, 3, 6, and 2. They enter the first level of our network at the exact time. At the exact same time, 3 comparisons happen. Node 1 compares 9 and 5. 5 is smaller, so it goes left. And 9 goes right. For node 2, compares 3 and 1. 1 goes left and 3 goes right. For node 3, compares 6 and 2. 2 goes left and 6 goes right. that all happen in just one single time step. Now they move to the next level. The new pairs meet. The algorithm repeats, smaller to the left, larger to the right. Even if we reverse the starting numbers, putting the heaviest first and the lightest last, the structure of this network forces the lightest package to keep finding the leftmost path. By the end of the network, the numbers will perfectly line up 1, 2, 3, 5, 6, 9. This proves that our algorithm is reliable. It works every single time, no matter the starting order. Let's look at the deep dive, the 0-1 principle. You might be wondering, Mirza, how do you know it works for every number without testing a million combinations? In advanced mathematics, we use the 0-1 principle. This principle states that if a sorting network can successfully sort every possible combination of just zeros and ones, it is mathematically guaranteed to sort any real numbers you give it. This saves us from endless testing and proof our logic is solid. So for the application, this 0-1 principle is a requirement for 21st century software engineering, for example. Now, look at our logical reasoning. We can mathematically prove the outcome. The smallest value will always take the left path at any comparison, guaranteeing it ends up in the far left final position. For the evaluation, a sequential sort requires 12 separate comparisons. By using this parallel heuristic, we complete the task in only 5 time steps. This evaluation proves that CT optimizes time and resources. If each comparison takes 2 seconds, we finish in just 10 seconds instead of 24 seconds. According to Ramos 2025, this kind of mathematical evaluation is what proves the value of our solution. We did not just find an answer, we engineered a highly efficient system. So this is the sequential sorting and the parallel heuristic based on the evaluation. Okay. So for sequential sorting requires 12 separate comparisons at 2 seconds per comparison, total time 24 seconds. But for parallel heuristic, utilizes 3 simultaneous stations, completes the task in exactly 5 time steps, total time 10 seconds. Conclusion, computational thinking optimizes both time and physical resources. So, why computational thinking is essential for non-routine problems? Without CT, solving this would be pure trial and error. You will just guess and check. But CT provides a systematic roadmap. It stops us from feeling overwhelmed. For systematic support, we learn that parallel processing, which is doing things at the same time, requires careful structural design, as some comparisons depend on the results of previous ones. CT provides a structured framework that prevents confusion when facing non-routine challenges. For meaningful insights, CT shifts our focus from just finding an answer to designing an efficient, scalable system. Integrating CT into math doesn't just find an answer, it builds a deep understanding of system structures and efficiency. This is meaningful learning pedagogical capacity or KPPB. As students, we are generating ideas and digital logic that mirror how real 21st century technology works. As you look at the screen here, the 21st century applications, which can we apply the sorting networking, okay, beyond our classroom. The first one, graphics processing units, GPUs. Modern video games rely on sorting networks to render millions of pixels simultaneously without lag. Second, database management. High-speed financial trading systems use parallel sorting to process infinite stock market data points in microseconds. And the third one, network routing. Routing. Global internet routers utilize this exact logic to ensure data packets reach their destination in the correct order, bypassing congestion. For reflection and conclusion, okay, as I reflect on this task, I see the massive effectiveness of the sorting network heuristic. It handles data beautifully. However, a critical thinker must also see the limitations. This network is a hardwired for exactly 6 items. If the logistics company suddenly needs to sort 7 items, this specific network fails. We would have to design a brand new one. True parallel processing also requires specialized computer hardware in the real world. But the learning value of this unplugged activity is amazing. It allows us to see invisible computer logic happening right in front of our eyes. As the computational thinking empowers us to confidently navigate and solve the complex, ambiguous challenges of the 21st century. To conclude, let's look back at our big idea and questions. We learned that decomposition allows us to see the simple rules hidden inside complex problems, and we learned that parallel computational thinking is the key to maximizing efficiency. As future educators, we must bring these tools into our classroom. The 21st century is full of ambiguous, non-routine problems. Computational thinking is the toolkit our students need to solve them. So this is the list of references I have used to design this slide. Okay, from Araya 2021, Lee 2022, Obando Montaya 2026, Brahmana 2024, Bawasi 2024, Ramos 2025, and Ravik 2026. So that's all from me. Thank you for lending me your eyes and ears. I will now end my presentation. Thank you.